Okay, so this is 4.6 number 3. I've already written out a problem for you. Here's the version of the problem that I pulled up. So I'm going to rewrite the function initially, take it out of rational function form, place it into power form so that I can more easily take the derivative. Once I have the derivative, I'm going to place it back into rational function form because that's going to be easier to work with. Okay, now I want to also factor this. Let's see, I'm going to factor this as, the easiest way to factor a rational function like this is to pull out the largest negative power. In other words, the biggest power in the denominator. And I might as well also pull out a negative because all three terms are negative. So I'm going to have a negative 1 over x to the 4th factored out. And then the remaining factors are going to be, well, essentially to create an x squared on the bottom, I have to multiply by x squared on the top, because x squared over x to the 4th would give you 1 over x squared. Okay, and I've already pulled the negative out, so this is a positive term. Over here, second term, again, I'm going to need a plus 10 because I've already factored the negative out, so it's we're left with a positive 10. And then I also need an x in that factor because x over, essentially x over x cubed, or sorry, x over x to the 4th would give you the x cubed. Okay, we're trying to arrive at x cubed. I've pulled out x to the 4th on the bottom. X divided by x to the 4th would give you 1 over x cubed. Similarly, in the last term, I've pulled out the x to the 4th from the bottom. I've pulled out the negative, so I'm just left with a plus 3. Okay, so that's my factorization of this derivative. And of course, we want to set this equal to 0 to find the critical points where the function's changing from increasing to decreasing. So this first factor is never 0. So negative 1 over x to the 4th equals 0 has no solution, right? And then this x squared plus 10x plus 3 equals 0 is quadratic. We'll have to, it doesn't look like a factor, so we'll use quadratic formula. So x would be negative b plus or minus the root of b squared minus 4 times a times c is 12 all over 2a. And I can simplify that a little bit. I can write that as, whoops, hang on, my pen's a little funky here. So it's negative 10. So essentially this is negative 10 plus or minus root 88. Root 88 is really what? Root of 4 times 22. And so I can write that as root 4 root 22 or 2 root 22. So that's plus or minus 2 root 22 over 2. Whoops. Again, my pen's kind of wonking out on me here. And so this is going to be 2 times negative 5 plus or minus root 22 over 2. And we're going to kill those 2's. Okay, so I've got negative 5 plus or minus root 22. Okay, and if I place those just to kind of get a feel for how big those numbers are in a calculator, let me grab my calculator here. Let's see. This guy is about, I've got negative about 9.69. And negative, I'm getting about negative 0.31, roughly, okay? Just to kind of get an idea. Now, to analyze whether the derivative is positive or negative, it's going to be good to get a graph of the derivative to see its behavior. Okay, so let me bring up my graphing calculator. Hang on a second. Okay, so here's my graphing calculator. I've gone ahead and entered the derivative into the calculator in the Y1 menu. And so now let's just get a graph. So I want to make sure I'm at a normal zoom because I sometimes zoom in and out on different problems. So I'm going to hit zoom standard just to get an initial look at the, so the 6th option there, just to get an initial look at the derivative. Okay, and as we expected, the derivative appears to have some kind of weird behavior around 0, and we expected that because here's the derivative, and the derivative obviously would be undefined at x equals 0. Okay. So, in fact, 0 looks like it's not even the domain of the function itself. Okay, so 0's, we have to be careful around x equals 0 here. Now, other issues, let's see. Can I see my zeros? Okay, I'm supposed to have a 0 right around negative 0.31 according to quadratic formula. So here it is. This must be that 0. I'm also supposed to have a 0 around negative 9.69. So I just want to make sure I've graphed things correctly. It looks, I mean, this goes negative, standard window goes negative 10 to 10. So right around there, it looks like I probably have a 0. Now this is a very, very kind of flat function out here. What I can do is I can quickly make a table. So first I'm going to check my table settings. So as long as I have kind of a normal starting point, that's okay. Delta table of 1. I might make my delta table 0.1 just so I can kind of zoom in a little bit. Delta table represents how much the rows of the table change by. So I'll make that 0.1, so we go by 1/10. Okay, and now I'm going to go second function table. And I'm going to kind of look out around negative 9.7, which is where we expect to have a 0, just to make sure that this is behaving normally and that we've graphed it correctly or entered it correctly. It's always good to make sure you're getting the expected behavior. So if I go out to negative 9.7, I see a very tiny negative value. At 9.6, I see a very tiny positive value. Okay, so it looks like we are changing signs there. So it looks like the graph is the graph. This table is based on how we entered the function, so it looks like we've entered the function correctly. If I want to basically see that 0 a little better, just to kind of give myself a little more confidence, I can go to Window, and notice we're supposed to have a 0 way out near negative 10, so I might make my x min like negative 15 or something like that, just so I can go a little bit past it. And then I have to kind of zoom in tight around that x-axis, and to zoom in tight around the x-axis, I'm just going to change my y max and y min a little bit. I'll make this like negative point, I don't know, I'll go with like 0.001. And I'll make my y max positive 0.001, just to kind of make sure that everything is looking like we expect it to look, based on what our solution is for the quadratic formula. Okay, and then my scale, I can't use a 1 for a scale anymore because I'm looking at such a narrow range. I'll make my scale 0.001s. Okay, and now I'm going to graph it. Okay, and so we do see crossing points here, okay, where we expected. Okay, so out near negative 9 and out near like the negative 0.31. Of course, this is super steep now because we're zoomed in so tightly to the x-axis. Okay, so we are seeing the expected behavior. Okay, that's good. All right, so now in terms of, let's go back to a standard zoom. So zoom 6 is the standard option. Now, essentially, if we, the calculator's going to, let's see, the calculator's going to disappear now because I'm going to type into the window here, but that's okay. Well, actually, you know what? Let me scoot this over a little bit. Hang on a second. Okay, so I've kind of scooted my work over a little bit so we can see the graph and the work. That might be a little more handy. Okay, so if I just quickly kind of sketch a little number line here just to kind of summarize my findings, I've got negative 5 minus root 22, which we said was approximately negative 9.69. And I've got negative 5 plus root 22, which we said was approximately negative 0.31. Now, in terms of the derivative, so we're going to look at the f prime behavior. If I look at the graph, again, it's a bit hard to discern what's going on. So if I'm going to go to a table. Again, I'm going to go second function table. Notice once I pass the negative 9.7 or 9.69, so once I'm at negative 9.7 and more negative, below that, in other words, more negative, I'm getting a negative derivative. Okay, so my derivative is negative out here. Once I pass negative 9.7, which is this root of the derivative function, I'm getting positive results. I can kind of scroll down and see some more numbers. I'm getting positive outputs for the derivative. Okay, so my derivative is positive here. Then now I have to be a little careful here because I should actually extend this a bit more. Sorry about that. Because we also want to think about what's going on at 0. Because at 0 we have an undefined derivative. Okay, so we can't really include 0 as part of any of the intervals of increasing or decreasing because we don't have a value for the derivative at all there. And so, but notice once I pass, so I'm going to go to table set again. And I'll start my table now. I want to look close to the negative 0.31. Actually, what might be easier here is just go with, I'll start my table at like negative, I'll start my table at 0. Oops, it doesn't want to accept an entry there. This emulator has been giving me some trouble. So let's see, will it accept? Let me just change my delta table then. Okay, I'll make my delta table 1. Let's see if I can make this a 1. Okay, it'll accept a 1 for some reason. Okay, so now I'm going to go ahead and make a table again. So notice that at x equals So again, when we're in this range between negative 9.69 and negative 0.31, we're seeing positive derivatives like we expected. At 0, we see an error, of course, because our derivative is all zeros on the bottom, and so we've got an undefined derivative. But between negative 0.31 and 0, I just want to double check what's going on in there. Okay, we saw it in the graph. Okay, it looks like it's negative here. Okay, it looks like the derivative function becomes asymptotic downwards. But we can just verify it on the calculator by zooming in a little bit, either zoom in using the zoom in function or with the table. Again, I should be able to go to table set, and I'm going to start at negative 1, and I want to go by 0.1s now. Okay, 0.1, whoops, let's try that again, 0.1, there we go. Now I'm going to make a table. And so notice I'm positive, 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 and then all of a sudden, once I get to negative 0.3, which is a little bit to the right of negative 0.31, all of a sudden I've got a negative derivative. Okay, and so I'm verifying that these are indeed negative until you hit 0. Now what happens after 0? After 0, we saw from the graph that it looks like the derivative function is again negative. Okay, so if we go back to the graph, there's what the graph looks like. So we're just verifying that we have a negative value for the derivative. Now, does this ever cross the axis? No, because if it did, we would have found another 0 in our analysis. When we set the derivative equal to 0, we would have found the derivative equaling 0 somewhere out here, and we did not. Okay, so the derivative is negative again here in this region. So my interval, so we have one increasing interval right here. So we're increasing on negative 5 minus root 22 through negative 5 plus root 22. Rounded or open endpoints, because at those endpoints themselves we're not increasing or decreasing. The value of the derivative is exactly 0 at those endpoints. Okay, and then for my decreasing intervals, let's see, I'll just go with a different color here. For decreasing, we're going to have 3 subintervals, 1, 2, and 3. 3 subintervals for decreasing for this function. We're going to have negative infinity through, it looks like negative 5 minus root 22, which is this piece. Then we're going to have negative 5 plus root 22 through 0, which is this piece. And then we're going to have 0 through infinity, which is this piece. Okay, so those are my increasing and decreasing intervals. Okay. Now, let's go on to concavity. So for concavity, we need a second derivative. So let me reset the screen here so we have some room. Hang on a second. Okay, so I just erased everything to give some more space. So here's my original function. This was our first derivative. If I use the power formulation rather than the rational function formulation, it's easier to take the derivative of the derivative to get our second derivative. And then I'm going to place that into rational function form. And then finally, I want to factor this. So again, I'm going to factor out, it looks like a 2 factors out of the numerators, and I can factor an x to the 5th out of the denominator. That's the biggest negative power, or technically the smallest power, the most negative, and out of the denominators. And so what's left over is what? Well, the 2 is gone, so I have 1. I'm left with a 1 and what? X squared. And then I'm left with a 15 here, and I need an x on the top, because an x over x to the 5th would give you x to the 4th. And then finally, I need a 6. Whoops, the pen keeps breaking up here. 6, and just 6, because the power, all the x to the 5th is all factored out of the denominator already. Okay, and so I want to look for where the second derivative is 0. Those are candidates for inflection points. You have to be careful. It's not always the case that where the second derivative is 0, you get an inflection point. Sometimes you don't. For example, like if you look at, just a quick little example here, just to kind of clarify. If you look at f of x equal x to the 4th, okay, then the derivative is going to be 4x cubed, and so the second derivative would be 12x squared. So if I set that equal to 0, to look for inflection points, I'm going to get x equals 0, right? Is that an inflection point? No, not really, because if you look at the second derivative, 12x squared, at 0, if I make a sort of a number line here, here's 0. If I go to, let's say, -1 or 1 and plug those in, I'm going to get positive 12 as my second derivative. So I'm going to get f double prime is at 1 would be 12, and f double prime at -1 would also be 12. In other words, the function, the second derivative is not changing sign. So this means I'm concave up here, and I'm concave up here. So I haven't changed sign. So just because the second derivative is 0, which is what we see here, second derivative 0, just because that happens does not automatically mean inflection point. You still want to check that your second derivative changes sign at the supposed inflection point. Okay, that the sign of the second derivative is switching as you cross over that point. Okay, in this case it doesn't, but if we look at the second derivative, essentially is just parabolic. It's just a parabola. There's my second derivative. And we can see that what's happening is we're having a 0 of the second derivative, but the second derivative is not crossing through the axis. So essentially the graph of the second derivative has to cross through the axis, through the x-axis, in order for the second derivative, in order for the location where the second derivative is 0 to truly be a inflection point. Okay, this is just a quick little example because a lot of students assume automatically that second derivative 0 means inflection. In fact, it does not automatically. You have to double check that you are. So this is not an inflection point because we're not changing sign. You have to check that it does change sign. You want it when the second derivative is 0. You kind of want behavior more like this, where you're passing through the axis. Okay, that's just a quick little look ahead. So if we look at our function from this problem, this is never going to be 0, right? So 2 over x to the 5th equals 0 has no solution, and no real number solution. And then we've got x squared plus 15x, whoops, sorry about that. Got to order a new pen for my writing pad here, plus 6 equals 0. Okay, so we're going to have to use quadratic formula on that. So let me do a little work here. Okay, so we're going to have what? We're going to have x equals negative b plus or minus root of what? B squared minus 4 times a times c all over 2a. Okay, so that's going to be negative 15 plus or minus, looks like root of 201 in this case, over 2. Okay, I can't really reduce that at all, unfortunately. Okay, and so I'm just going to kind of just get quick ballpark estimates of this. Okay, so I'm getting, let me grab my calculator here. All right, this guy is approximately negative 14.59. This guy is approximately negative 0.41. Okay, and so let me make a little room here. Hang on a second. Okay, so here I've brought up my calculator now, and I've placed my second derivative into the calculator in y2 position. So I'm going to turn off y1. I'll leave it in there just in case we want to look at it again. So I'll put the cursor over the equal sign, hit enter. So that eliminates that from being graphed, but it's still in the memory. Okay, now I'm going to hit a standard zoom. So zoom 6 for a standard zoom. Okay, and there's my second derivative. Okay, and so let's see if we're seeing what we expect. We expect to see a 0 at negative 0.41, which looks like to be about here. I expect to see a 0 at around negative 14.6. So that would be somewhere past the screen. So just to verify, again, we can trust things, but, trust but verify. So I'm going to just make sure I see it. Okay, so I'm going to go to Window, and I want to go out past negative 14.59. So I'll go out to negative 20 in the x direction. Okay, now to see that, again, we're going to have to kind of zoom in tight around that x-axis. So that means my y's have to be much tighter. So I think last time we used negative 0.001. That seemed to work okay. So we'll try it on the second derivative. It's a little slow to type things in on the emulator. And then, whoops, I didn't want to do that. Turn that back off. Sorry about that. Window, we were entering the window. Okay, we wanted to I'll make my scale 0.001 just so that we have, I can't have a scale bigger than the range of the y's. Okay, so I'll make my scale 0.001 or even smaller, but I just want to get a quick picture. Okay, so now let's graph it and let's see if we're seeing that crossing point. And there we see it. Okay, so we're seeing that the second derivative is indeed 0, right around where we expected, and also here. Okay, so let's go back to a standard zoom again. So zoom 6, sixth option is standard zoom, right there. And just to get a quick picture again. And notice that, again, the second derivative, of course, is also going to be undefined at 0. So there's so that's to be expected. But we are seeing that it looks like the second derivative is negative in this range, okay, and then negative again over here. Okay, so let's to kind of look out near the location we were expecting. So negative 14.59 is where we expected the 0 to be of the second derivative. I'm just going to quickly go to table set. And just to make sure everything's okay, I'm going to start my table at about negative 15, if it'll let me, because the emulator's acting kind of weird. Okay, and I'm going to make my delta table 0.1, just so we can kind of zoom in around that region a little bit, and then make a table. Okay, so I'm seeing that out past negative 14.59, so negative 14.6 onwards, I'm seeing negative derivatives. Okay, so I'm going to summarize that. Sorry that the calculator's going to disappear for a minute, but that's all right. We can bring it back. Okay, so here's negative 14.59, so that's essentially negative 15 minus root 201 over 2, which was approximately negative 14.59. Here is negative 15 plus root 201 over 2, which is approximately negative 0.41. And then, of course, 0 is important as well. Okay, so let me kind of just extend this a little bit. Okay, so this is for my second derivative. Now, so what we see from the calculator, let me bring that back up real fast, is once we get past negative 14.59, we have a negative second derivative. So out here is negative, so let me enter that information. That's negative. Bring back the calculator. Okay, and now the between over here, it looks like we're positive. Okay, so our outputs are positive once we get to the right of negative 14.59, so negative 14.4, etc., or even negative 14.5. We're seeing positive second derivatives. Okay, once we get to negative 0.41, it should go negative again. So let's just check that in our calculator. Okay, so what I'm going to do is go to table set, and I'm going to start my table right around negative 1. Okay, and go by 0.1s. So my delta table of 0.1. Let's make a table. Okay, and so I'm seeing that I am indeed positive, positive, positive until I hit, this is around 0.41, negative 0.41. So once I hit negative 0.41, once I get past it, like negative 0.4 onwards, I'm seeing a negative second derivative. Okay, so this is all negative in here. Okay. Okay, so I've just kind of slid my screen over a little bit so I don't have to keep bouncing back and forth, a little nicer. And so if I just look in the positive region, we're seeing positive values for the second derivative. If we look at the graph, we're in this region here. We can be assured that there's no crossing points out here because we would have found them by setting the second derivative equal to 0. We did not. So it's just kind of asymptotically approaching a second derivative of 0, but not reaching it. So I have a positive region out here for my second derivative. Okay, and so remember, concave up, so let's just kind of summarize here. Concave up is where the second derivative, so when the second derivative is greater than 0, we're concave up. Okay, we're increasing with an increasing rate of change is what that means. Okay. Whoops, it's hard to write at the end of the screen here. Increasing rate of change, sorry about that. But anyway, we're concave up. And so where is that concavity going to happen? Where are we concave up? It looks like between these two roots right here. Okay, so this would be from negative 15 minus root 201 over 2 through negative 15 plus root 201 over 2, union from 0 through infinity. Okay, again, we're not including the endpoints. And for concave downwards, okay, we're concave down when the second derivative is less than 0, then we're concave down. We're concave down essentially is increasing with a decreasing rate of change. Right, so that would look like this. So concave down, increasing with a decreasing rate of change would look either like this, okay, or so you're basically it's decreasing rate of change. Okay, so you can be either increasing with a decreasing rate, or you can even be decreasing with a decreasing rate like this. Okay, for concave down like this. Both of those are concave down. We're increasing with a decreasing rate or decreasing with a decreasing rate. Are both concave down. As long as the rate of change, the second derivative, is negative, you're concave down. Okay, so this would be, these would have positive first derivatives but negative second derivatives. This would have negative first derivatives and negative second derivatives. Okay, with the increasing rate of change, we should actually stipulate that as you're either increasing with an increasing rate like this, or you could be decreasing with an increasing rate for concave up. So that would look like this. So decreasing with an increasing rate would look like that. Your function's going down, first derivative is negative, you're decreasing, but the rate at which you're decreasing is becoming less negative. So it's increasing, right? When the slopes are becoming less negative, the slopes, which are already your first derivatives, so remember, all your slopes along here, if you kind of just draw yourself a little slope, like a little tangent line, so here's some tangent lines, tangent line, tangent line. Those tangent lines are getting less negative. The slope of the tangent already is the first derivative. And so those first derivatives are getting less negative, so they're increasing. Less negative means increasing, okay? Like my bank account, right? The only way my bank account increases is when it becomes less negative. Boom, boom, math joke. But anyway, well, unfortunately, it's a little serious. But anyway, so less negative slope is increasing, so you're decreasing with an increasing rate, concave up, or more positive. So either your slopes get more positive, slope is already a first derivative, so your first derivative is getting more positive, pointing up steeper, and so therefore your second derivative is greater than 0 there, or your slopes get less negative. So we're just kind of reviewing the concept here a little bit. Your slopes get less negative, meaning they're pointing down less steeply, so they're getting less negative, which is the same thing as increasing. Okay, it's the slope. The second derivative is increasing. Okay, the first derivative or function is decreasing, but the slopes are getting less negative, meaning the slopes are increasing. The slope of the slopes are increasing, getting less negative. In other words, the first derivative, the slope already is a first derivative, so the first derivatives are increasing. When the first derivatives increase, that means your second derivative is positive. Okay, so second derivative positive checks for either of these scenarios. Second derivative negative looks for these other scenarios. Okay, so if we kind of talk ourselves through it here, here we're going to have the slope is very positive and then slightly less positive. So the first derivatives are getting flatter, less positive. So f prime gets less positive. Sorry about that, less positive, which means the first derivative is getting less positive, so the first derivative is decreasing. And you can see that it looks concave down or more negative. The slopes or first derivatives are getting more negative. Okay, so the slopes or f primes get more negative. So that means decreasing. Okay, so when the slopes decrease, the first derivative is decreasing, so the second derivative is negative. Okay, because the slopes already are first derivatives. And so this condition, second derivative less than 0, checks for either of these situations. Okay, so that's just kind of a summary here, but to go ahead and answer the rest of the problem, obviously we're going to be concave down where? My concave down intervals are going to be this guy and this guy, right? So we're going to have negative infinity through negative 15 minus root 201 over 2, union negative 15 plus root 201 over 2 through 0. At 0, we have the derivatives, the second derivative is undefined, so we cannot include the 0 as a place where anything definite is happening. And then also for concave up, obviously, let me change colors here. For concave up, it's going to be these regions, right? So this region here and this region here would be concave up. So we're going to have the region between the two roots and so negative 15 plus, I'm sorry, minus root 201 over 2, comma, negative 15 plus root 201 over 2. That region, union, this region out here, 0 to infinity. Okay. And there we go. Okay. Okay, so just as the last step in this problem, we don't have to do this, but just to kind of make sure, you know, everything kind of ties together, let's just analyze the function itself. So here's all the information we found. And of course, we found that the, let me write down the intervals we found. So give me 1 second here. Okay, so I've summarized what we found on this problem. And now let's just take a look at the function itself, just to see that this all ties into the graph of the function. So let me bring up my calculator. Okay, so here I've gone to y equals, and let's see, I've got, that's my first derivative. Let's see, that's my second derivative. I'm going to turn off the second derivative, and I'm going to type in the actual function itself, which is just 1 plus 1 over x plus 5 over x squared, and plus 1 over x cubed. Okay, and so that's my function. I'm just going to go to a standard zoom. So zoom, 6th option. Okay, so we're seeing kind of a slightly complex behavior here. It's kind of a little hard to decipher what's going on. So let me kind of slide this over a little bit. Okay, so what we can do is first let's kind of zoom in on this region in here. So for that region, it looks like maybe the area of interest is maybe from -2 to 2 in the x direction, but I need to look a little bit higher. So I'm going to hit window, and I'm going to go from -2 to 2 in the x direction, and I can leave 1 as the scale. That's fine. But in the y direction, I want to go higher. I want to go up to maybe 20. Okay, and we can make my scale at 2, so we don't have too many hash marks. Okay, and let's hit the graph. Okay, so what we're seeing here is the function's increasing, increasing, and then all of a sudden decreases. So this would correspond to the increasing interval. That would correspond to this transition right here. In fact, I should have slid this over a little bit. Let me slide this over. Hang on a second. Okay, so I've kind of slid things around a little bit so it's easier to see. Also, let me just enter the decimal approximations for some of these endpoints to make the discussion a little bit easier. Okay, so I've kind of entered in the decimal equivalents or rough equivalents of these radical or irrational expressions. And let's just kind of make sure everything looks the way it should. So first of all, I should be increasing from -9.69, which is way out to the left, which we can look at later, up through about -0.31, which would be about here. Okay, so I'm increasing through here, and then I'm decreasing from -0.31 to 0, so this is a decreasing interval, which we see right here. And then we're also decreasing again from 0, which is our, starting just past 0, so it's an open interval at 0, meaning we start just past 0, all the way out to infinity, we're decreasing. Okay, so we verified, this makes sense. Let me kind of, I guess we'll verify things in gray here. Okay, so this looks good, this looks good, this presumably looks good. We can check a little bit further out to the left. Okay. What about, and then increasing from -9.69 to -0.31. It does look like we're increasing here, okay? But we can still verify these guys when we look out further to the left, okay? But let's look at the concavity now. That's really interesting. On the concavity, we're concave up because we're increasing with an increasing rate of change through about here. Okay, let me change to a different pen that I can use to draw on the calculator screen. So I'm concave up, meaning increasing with an increasing rate of change through about here. Okay, then all of a sudden the slopes start getting less positive. Okay, when the slopes get less positive, that means I'm increasing with a decreasing rate of change. And here I'm decreasing. I'm decreasing with a decreasing rate of change, meaning more negative. So in other words, I'm going from a smile to a frown, essentially. Increasing faster and faster, and then I'm increasing slower, 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 not even increasing at all right at that critical point, and then actually decreasing. So my slopes are getting less positive and more negative through here. The slopes here are less positive, meaning decreasing, and then more negative, meaning decreasing. So this is concave down. Here my slopes, which are my first derivatives, are getting steeper, meaning the slopes or first derivatives are increasing, so the second derivative is positive. So there is an inflection point right around here. Okay, so let's label that inflection point. And that's got to be at the point where we're changing concavity from up to down, which would be, let's see, so we're concave up through about negative 0.41. We're concave up, and then all of a sudden we switch to concave down right at that point. Okay, so we're transitioning right here from concave up, we're ending there, and we're starting a concave down region right at about 0.41. So this would be negative 0.41 is the transition point. And notice the maximum, which is where we transition from increasing to decreasing, is at negative 0.31. So that makes sense on the graph, right? If I kind of label that, let's see what's a good color for that, something that's not on the screen yet. We're kind of running out of colors here. I guess I'll go with yeah, dark green, I guess. So this point right here, this maximum, is at an x value of negative 0.31. Okay? It's a little hard to write in there, but negative 0.31, which is this guy. Okay? So we're transitioning from increasing to decreasing right there at negative 0.31, but our inflection point is at negative 0.41. We're transitioning from concave up to concave down. Okay, so that all makes sense. Now we just want to look way out to the left on our function. Now, before we do that, on the right side, we're just strictly decreasing. Right, we're strictly decreasing after that asymptote. Okay, we're strictly decreasing. So we're decreasing from 0 to infinity, which makes sense on the graph. And also in that region from 0 to infinity, we're constantly concave up. Why are we concave up? Because we're decreasing with a increasing rate of change. Okay, in other words, if I drew little tangent lines in there, let's see what's a good tangent line color. I don't know, I guess go with kind of like a reddish orange. All right, so my tangent line's pointed down pretty steep. Over here, my tangent line's a little bit less negative. Okay, a little bit less negative. We're talking about the steepness of these lines, not the heights. Okay, so the steepness or value of the slope of the tangent line is getting less negative. The slopes are getting less negative, meaning the derivatives are getting less negative, meaning the derivatives are increasing. So the f prime values are increasing in this region, okay, which means the f double prime is positive, okay, which means we're concave up, okay, getting less negative. A less negative slope is really an increase, okay. Now let's look way out to the left. Let's look way out by around negative 10, negative 15, around that area, okay, like around here. This is near negative 10, this is near negative 15. So let's change the window. Okay, so I'm going to go to window here, and whoops, hang on a second. Okay, so let me actually clear that drawing here. Okay, and let's change the window. Whoops, hello. Hang on one second. Okay, I think I got it straightened out. So let's hit window, and let's go maybe from negative 20 through, I don't know, let me see. Actually, I kind of worked it. Let's do window negative 20 through maybe negative 10. Okay, and of course, I'm going to want to, if we graph that real fast, it's going to look pretty boring, okay, because the heights are very small there. So obviously, I need to change the y values, okay, so let me change the y values. Let's try to get a good window value on a function that's not changing very much. It helps a lot instead of just kind of plugging around. Let's actually generate a table real quick out in that region. Table helps you get window. That's a really good skill. Okay, I recommend it highly. To get a good window, unless it's kind of obvious, then obvious cases are just obvious. But if it's not an obvious case what the window should be, make a table. Okay, so I'm going to go to table set. I don't need to be super precise here. I just want to get a rough idea of what table to use, or what window to use. So I'm going to start at maybe negative 15, which is kind of right in the middle of that region out in the negative area. And I'm going to go by ones, not by point ones, because I don't need to check super closely. I already know what the behavior of the function is. I just want to get a quick look at the y values to see what to set the window at. Okay, so now I'm going to make a table. And I'm noticing that the y values are varying from about 0.949 through, if I go to negative 20, through about 0.962. So what if I go from about 0.94, we want to go a little bit below the lowest point we're interested in. So if we're interested in 949, I'm going to go to 0.94 as my Y min. Okay, so again, the table is helping us get the right window. And then if I go to -20, at -20 my height is about 0.96. So I'll go up to about, I don't know, 0.98. Well, actually, I'd probably go a little higher. Let's go to maybe like 0.99 or something, or 1, make it 1. So if I go to 1 as my upper Y limit, and for my lower Y limit, maybe about 0.94. Why 0.94? Because here at -10, I'm at about 0.949. So I'll go 0.94 to, how about 0.94 to 0.98? Okay, so let's try that, 0.94 to 0.98. So I'll go to window, and for my Y min, I'll go 0.94. For my Y max, I'll go 0.98. And my scale, I'll make it 0.01s. Okay, and let's get a graph. Okay, so we're seeing we could get a little bit better than this. Let's see. Okay, and the reason we can get better is, if you think about it, we're catching the -15 or -14.59, but we're not catching this guy yet, -9.69. We wanted to look at the activity around there. So I'll make my X max, instead of -10, let's make it like -5 or even 0. Okay, just so we catch that behavior. Okay, because I want to make sure to catch this as well as this. So now let's take a look. Okay, notice our Y part of our window is working perfectly, and we're seeing exactly what we wanted to see. So using the table to set the Y values is really handy. Okay, and so notice what we're having here is we're decreasing through this critical point, right? So we're decreasing basically through -9.69, which is where we are here. Okay, and then we're increasing from -9.69 through -0.31. So this is at -9.69. Okay, so let me grab my pen here. So this critical point would be at -9.69, or so, or -5 minus root 22. So we're at -9.69. right there. And then what about the concavity questions? Well, it looks like from -14.59, well, from negative infinity through about -14.59, we're concave down. So that would correspond to this region here. Concave down. Now, it doesn't look very concave down, but it is. Okay, we could zoom in further on this region to show it's concave down. Okay, and then it looks like we are transitioning. So at -14.59, right here, we're transitioning from a concave down region into a concave up region. Okay, so at from -14.59 through way out here at -0.41, we're concave up. Okay, so we'd be looking like this, concave up. Okay, so this concave down region is not beautifully displayed. We could kind of go tighter in there to show that it's concave down, but we are getting a basic idea of what's happening here. And of course, our inflection point right here is at, so we're inflecting at -14.59 roughly. Okay, so that's the rough value of the inflection point. So we could kind of tighten in the zoom here to show that it's actually kind of curving downwards, concave down. Okay, but anyway, that's kind of the behavior. And so overall, we verified by first analyzing the first and second derivatives to get the precise values of these points where we're changing the increasing or decreasing nature of the function or the concavity, and then verifying this through a graph of the function. Now notice, if we would have just graphed the function by itself without doing the other analysis, it would have been almost impossible to locate all these points. So, sometimes it's tempting to say, well, I can just go graphical, purely graphical. In this case, it wasn't that easy. You really needed to do the analysis of the first and second derivative to find all of these, the critical points and also the inflection points where the concavity is changing. Okay? And also remember that, we need to show, in order to show that you have a inflection point, you need to show that the the second derivative is truly changing sign. Okay? So, for example, here we see, let's say, what's a better color here? I don't know, we'll go with like a purple. Okay, so we see that we're changing from concave down to concave up here at this location. And the second derivative, we technically should show that the second derivative is changing sign. And the way we showed that was we showed that on the table, if you remember. Right, when we viewed the table of the second derivative function, we saw that right around this point, on one side of the point, the second derivative had one sign. On the other side, it had a different sign. Okay, so just don't be fooled, because every so often you'll get a case like I showed you earlier where you get second derivative 0, right? Like the case of x to the fourth, right? The second derivative of x to the fourth was 12x squared, right? And so that's my f double prime. So if you have f of x equal x to the fourth, as an example, f double prime of x would look like this. And so your second derivative is 0 there, but you're not changing sign. If you would make a table of the second derivative, you'd see positive results on both sides because you're concave up on both sides. So you have to be careful. You have to check a table when you find your inflection point or your possible inflection point. Check a table of the second derivative. Put the second derivative into your y equals menu. Right, put the second derivative in, which was right here. Sorry, let me clear some of that drawing here. Okay, so the second derivative was here. We made a table, and we showed, using the table and making my delta x 0.1, that we were actually transitioning concavity at this point. So for example, if I go, let's just remind ourselves, if I go to table set, and, whoops, hello, hang on a second, let me turn this off. Okay, so if I go to table set, and I'm going to look right around negative 15 as my starting value, just to remind ourselves what we did, and make my delta table 0.1. So I'm just proving that that's an inflection point, and then I want to make a table. So notice at negative 14.6 roughly, we're transitioning. Okay. So actually I'm graphing this. The reason we're not seeing a transition is because I'm graphing y3. I should be graphing y2 here, so hang on a second. Okay, so let me turn off y3 and turn on y2, which was my second derivative. Okay, let's try that table again. Okay, so notice at negative 14.59, so negative 14.6, we go negative values, and prior to that, or at higher values, negative 14.5 onwards, we're getting positive second derivatives. And so we're proving that this is indeed an inflection point. We're not getting a pseudo inflection like this. Okay? So we actually do change sign on the second derivative. So you have to have, so for inflection point, just remember, for an inflection point, you have to have the f double prime of x must change sign. Okay? It's not enough to just prove that it's 0. You have to show that it changes sign on each side of that 0. Okay, that's it. So we've kind of analyzed this function very completely. All right, there we go.